That's the easy one. Can you tell me what to do? Time constant, right? Simple question, straightforward question. You know the time constant? Very good. So let's see if it gives the answer. R is 0.5. Mega ohm means 10 to the power 6, right? And resistance is, C is 90 microfarad. You see the beauty is this. Okay. So half of 90 is 45. Well, 0.45, right? No, 45, sorry. 0.5 means half. Okay. That's very quick. Number 16. The proton moves along its axis. It enters a region in which there is a magnetic field directed at an angle of 30 degrees with the y-axis and lying parallel to the yz plane. Find the initial direction of the magnetic force on the proton. So we have to find the direction only, not the magnitude. You know how to do this? Okay. Can you visualize this? You have no issue with visualizing the space 3D? So you're hesitating. I mean, you have a problem. Okay. So, let's imagine this is your y-axis, and this is your x-axis. What will be the z-axis? It will be like that. So what we have here. So y-axis in this plane, x-axis also in this plane, and y-axis is coming out of the board, the positive side. The negative side of the z-axis will be into the board. X and y are there. Z is out, positive Z, negative Z is in. But when you draw it, you cannot really do that. Can I draw like this? So that's why we have drawn it like this. This actually it is coming out towards you. Okay. You have a pen or something? I need something different. Thank you. I'm going to use this for the velocity. So the velocity is in the y-axis. That means on the parallel to this, right, y-axis, this way. And this is for the magnetic field. Magnetic field is like this. They are both in the same plane as the board, which is xy plane. You should understand me when I say xy plane, what I'm referring to, right? Here the xy plane will be the plane of this whiteboard, okay, smart board. So what we have here is something like this. This is in this plane, okay, let me see, this is my whiteboard. And you are asked to find the direction of the magnetic force. So this is the velocity, this is the magnetic field. So how do you do that? You take your right hand and put the four fingers in the direction of the first vector, V cross B, right? The equation is the magnetic force is Q and V cross B. So we need to get the direction of this. Then if Q is positive, fine. If Q is negative, whatever the direction we get for the V cross B, I have to flip it by 180 degrees. Okay, you know that. Okay, so how do you apply the right hand rule? Now, can you do it? Put your fingers, the four fingers without the thumb, in the direction of the velocity. This is the velocity. This is the magnetic field. So you have to choose the velocity first and put in the direction, and so that you are curling your finger in this plane. If you keep it like that, you are curling the finger not in that plane, right? So keeping like this will help? No, no. If you keep like this, your curling is in this plane, not in this plane. Do you understand me? Okay. If you keep like this, are you curling it in this plane? Yeah, your curling is happening in the plane perpendicular to this plane. Is very clear to you? Okay, right? So if you try, okay, I'm going to, okay, I told you put the fingers in the direction of the velocity. So you'll say, oh yeah, that is what you told me. I'm going to keep it. What is wrong with this? You can you bend it towards the magnetic field? It's going somewhere else. These fingers must approach magnetic field. If you go like this, can you ever meet the magnetic field? No, it is here. So you have to keep the fingers along vector V, but you should be able to bend it towards the magnetic field. So that we have to keep it like this. Then you can bend. Now don't look at the thumb now, but pay attention to what I'm saying, right? Then you can say, okay, I can do like this also. Then also I'm curling in this plane. Again, you can say I can bend and I can reach. But why it is this, not this? Yeah, it is close. If you bend, you have to move a big angle. If you keep like this, you are moving quicker. You will reach it faster. So you have to curl it with the smaller angle. Okay, not here. You can still you are bending in this plane, but you have to move a big angle. But if you move like this, you are moving a smaller angle. Okay, then look at the thumb. That is the direction of V cross B. Therefore, because a proton Q is positive, that is also the direction of the magnetic force. Clear? So the answer is therefore what? Look, is this B in the XY plane? No, it is in the YZ plane. So it's like this. I made a mistake when I said B is like this, because I didn't read the question. The B is in the YZ plane. So you can kind of see it, right? It is in this plane. Oops. The plane that is perpendicular to the whiteboard. So B is like this, not like this. Why did this correct me? Okay, anyway. All right. So now tell me what will be the direction. Like this, right? Yeah. So the plane you will be bending is in this plane, the plane made by V and B. Want me to repeat it, or you're okay with this? You want to repeat? No, it's fine. Okay, so V cross B, the thumb is pointing to the positive X direction. Okay, that's see. The magnetic field is making now theta equal to 30 degrees, but it is in the YZ plane, not in the XY plane. So it's actually B is like this. I was keeping like that. It didn't stop me. All right. Yeah, sorry about that. Okay, so. The question is about finding the direction. So magnetic force, okay, on the proton. First, you have to find the direction of this. by applying the right hand rule, then it is not going to be the magnetic force direction, may or may not be, depending on the Q. If Q is a positive charge, it will not change anything. But if Q is a negative charge, like an electron, whatever the direction you get from this, you have to make it 180 degree, the opposite direction. Okay. Suppose it's electron, the answer will be negative minus x. A charged particle that is moving in a static uniform magnetic field, okay, you know that when there is a charged particle, if it is moving in a magnetic field, it will experience a magnetic force, okay. So you know that for a fact. Now there are this statement, only one of them is a correct statement. Let me start with A. May experience a magnetic force, but its direction of motion will not change. No, that's not true, because the force can be any direction. Sometimes it will be in direction, not in the same direction as the velocity. It is perpendicular to the direction of the velocity. It will be perpendicular to both the velocity direction and the magnetic field direction. That means it will change in the velocity direction, okay, because going some direction, but there's a magnetic field perpendicular to the velocity, so that will change the direction. It will push. If something is going like this, and I apply a force perpendicular to that, it is, of course, it is going to change the direction. So that is wrong. May experience a magnetic force which will cause its speed to change. No. When the force is perpendicular to the velocity, the magnitude will not change. It will only change the direction of the velocity. So therefore, that is also wrong. We'll always experience a magnetic force regardless of direction. That is not true. If the magnetic field is parallel or anti-parallel, 0 degree or 180 degrees, with the velocity direction, then there will be no force. That means it will not change the direction. So to say that always make this guy wrong. Yes, it will change. If you have a perpendicular component, velocity has a perpendicular component in the magnetic field, it will change. But sometime it may be in the same direction as the magnetic field. Velocity, if it is in the same direction as the magnetic field, it will not change. So to say always will make this statement wrong. Let me look at E. No, because this is correct. May experience a magnetic force, but its speed will not change. That is a correct statement. Okay. So when a charge is moving in a magnetic field, yeah, it will experience a magnetic force provided the velocity has a component perpendicular to the magnetic field. If it is not, then it will not change. So this statement is completely correct. Question number 18. The path of a charged particle moving with velocity vector perpendicular to uniform magnetic field will be a circle. So because every time the direction of the velocity will change, so it will push, so it will start describing a circle when the velocity is perpendicular to the magnetic field. If it has component in both directions, there is a component perpendicular as well as parallel, then it will start doing a helix. Number 19. A circular wire loop of area 0.36 meters square, so that is the area of the loop. Carrying a current is placed in a magnetic field of magnitude 0.5 Tesla. The magnetic field is also given. And the area of the loop is also given. The current in the loop is 2 amperes in the direction shown. It's a current that's flowing. It's 2 amperes. The magnetic field is in the zy plane and makes an angle of 30 degrees with the z-axis. So you have the magnetic field, it's in the zy plane, it's making an angle of 30 degrees with the z-axis. Find the magnetic moment, one, and find the magnetic torque. Two question in one. We have to have two things in the same question. You have to find the magnetic moment and then the magnetic torque. So somebody tell me what is the formula for the magnetic moment? Come on, guys. Magnetic, what is the equation for magnetic moment, Sulaiman? Kinetic? Yeah, sure. Check the formula sheet. Yeah. Magnetic moment, if a loop wire, okay, it can be any shape, but it should be a closed wire. It has a magnetic moment. If there's a current through that loop, because of that current in that loop, it will have what is called a magnetic moment. The equation is N is what? Number of what? Number of loops. Okay, how many? You can have not a one single loop, it can be coils, many loops. So N is the, what is I? Current in the loop. What is A? Area of the loop. Okay, so simply substitute and get the answer. So what is the means single loop. Okay, so N is equal to 1. I is 2 amperes. Area, this is a, what is the formula for the area of a circle? So it's a circular loop. What is the form? Pi r squared. How much is R? Sorry, we don't, yeah, it is completely given, right? So we don't know what R is. Does it matter? No. He is giving the area right away. So we just substitute. So this will give us the, you take the calculator and you will find this answer. Okay, since we have the solution, we can check. So you get the mu. But you need to give the direction of mu also. Okay, because he is saying 0.72, 0.70, all of them the same. So we are trapped here. You need to get the direction. Mu is a vector. The magnetic moment is a vector. It will be the direction of the area of the loop. Direction of the area is perpendicular to the area. So it can be either positive z or negative z. Which is the correct one? Why? How do I know? Yeah, of course, because the answer, but let's say you don't know the answer. I didn't give you the answer. You need to, because it could be either A, which says negative x-axis, no, sorry, positive z-axis, or B, which says negative z-axis. And there are other choices, okay? Well, okay, is either positive z or negative z. Which one is correct? It should be perpendicular to the plane of the loop, right? The loop is in the xy plane. So the perpendicular to the xy plane is either positive z or negative z. Yes, answer is positive z. How do you know that? No, direction. Yeah. How do you do that? Look at the current, right? Curl your finger. No, the right hand rule number 2, right? I mean, look at the circulation of the current, right? So take your right hand, you bend the current in the direction, bend the fingers, curl the fingers in the direction of the current. Is it correct like this? No, because the current is going like this, right? You see that? From looking from above, the current is flowing counterclockwise. So if either you have to keep like this or keep like this, only two choices. If I keep like this, is my finger is curling in the direction of the current? No. If I keep like this, yes. Okay, looking from above, it is counterclockwise. So the current is flowing here counterclockwise. This is the direction of the current. So then look at the thumb. Thumb is pointing in the positive Z axis. So this is correct, this is correct, and this is correct. We have either A, C, or E. But we have another part, right? We also have to find the torque. What is the formula for the torque? Tell me, you can check the formula sheet. Yeah, it's the vector product of magnetic moment into vector product, no normal product into magnetic field. This is how you get the torque. So magnitude will be mu, magnitude of mu, magnitude of B, sine of the angle between the vector mu and vector B. That's how you get the vector product. Do we know mu? Yes. Do we know B? Yes. Do we know theta? What is theta? The angle between B and mu. We know that, right? So substitute. Mu we already found 0.72. B 0.5. Theta 30. When you take your calculator and calculate it, you will get 1.8. Yeah, 0.18. Now you eliminate this. C is out because, okay, so you have either A or E. Okay, now that depends on the direction now. What is the direction of tau? It's like the magnetic force, right? Because you have two vector products. So you apply the right hand rule on mu and B. Like V and B, instead of V, we have the mu. What is the direction of mu? Z axis. And what is the direction of B? It making, now I have to imagine, let me say, I mean, this is a little tilted. Let me make this as my Z axis, this as my Y axis. Okay. I'm going to put the Z axis on the board and Y axis also on the board. What is X axis? X axis coming out of the board. Right. Now your mu is like this. Okay. And your B is making an angle of 30 degrees with mu also in the ZY plane, So I'm going to use this pen as mu, and this pen, okay, the board pen as B, mu and B. What is right hand rule? Take your right hand, put your fingers in the direction of the first vector, which is mu, and you curl it towards B and look at the thumb. Thumb is pointing in. In direction means negative x. Okay. Therefore, A is the correct answer. This is negative y. Wrong. The current in a long straight wire produces a magnetic field. The magnetic field lines is a concept, and it will be circles around the wire. Circles around the wire. So if the current is up, the circle will be going counterclockwise. If the current is down, the circles, the direction will be clockwise. But here is only about, all these are wrong. Number 21. A long wire lying along the y-axis carries a current I in the positive y direction. Okay, now you see this, you have to be able to understand this axis. X and Z in the board. Okay, XZ plane is the plane of the board. So what is the y-axis? Y-axis is perpendicular to the board. The positive y is into the board. Positive y is into the board. Negative y is out of the board. You should be able to visualize it. It's very important. Okay. So X is to the right on the board. Z, positive Z is up on the board, and positive y is into the board. Negative y is out of the board. Right. So we have a wire which carries current is in the y-axis. Okay, and it is in the positive y-axis direction. So if this is the direction of the current, so the wire is carrying a current into the board. This, let's say, imagine this is the wire. Okay, let me use this. This is the wire. So the current is going into the board in the positive. This is actually into the board, but I cannot draw it here, right? I mean, it's like this. Okay, but I have to show it in a perspective view like that. Right, now, in which direction is the magnetic force exerted on the particle at that instant? There is a positive charge here. There is a positive charge here. Let me use. Here, there is a positive charge. Okay, and it is also going into the, it has a velocity into the board, and there is current wire. There is a current wire here, and current is I. It is also into the board. There's a current wire here and a charge here, and the charge is moving into the board, and this wire is also carrying a current into the board. Now we say that, okay, this is a charged particle. It will be affected by the magnetic field created from this current carrying wire. So at this point, there will be a magnetic field from this wire on this particle. So that particle will experience a force given by this equation. Right, so that's a charged particle which is going into the board in the positive y direction. The velocity direction is positive y direction, and there's a magnetic field coming from this current carrying wire. So I need to know the direction of that magnetic field. How do I get the direction of the magnetic field? No, magnetic field line from the wire, okay? So the wire, the magnetic field lines will be circles around this wire. And we need to know the direction of the magnetic field. Okay, of course, circles like this. What is the direction? Let me draw the current here. This is the current. Current is going in. So the circle will be like this, concentric circle. This is the charge is here, our charge is here. And this is the current. Now, which direction will be the magnetic field? Is it clockwise or counterclockwise? Yeah, clockwise. So at this point, the magnetic field will be tangent to the circle. So now I know the direction of the magnetic field. Let me use green perhaps. So the magnetic field direction is like this. The velocity direction is into the board. Now we are ready to find the magnetic force. So let me use this pen for the velocity and this pen for the magnetic field on the charge. This is the velocity. This is the magnetic field. How do I get the magnetic force? V cross B, right hand rule. V cross B, my thumb is pointing to the left, which is negative x direction. Is the charge positive or negative? Negatively charged. So you get the V cross B to the negative x direction, but because it is a negative charge, it will flip, so it will be positive x direction. Okay, this is in a sense a bit challenging question if you don't know how to apply the right hand rule. Okay, the two concepts also, because you need to know what is the magnetic field direction. For that, you need to know that current carrying wire, the magnetic field will be circles, and whether counterclockwise or clockwise, you have to determine by that. Question 22. According to Lenz's law, the direction of induced current in a conductor will be that which tends to produce which of the following. That's just Lenz's law. It will be opposing the change. So that's why the answer is B. Opposing the effect which produces it. Okay, so Lenz's law says the direction of the induced current in a conductor will be such that it will oppose the effect which produces it. Okay, now these are Lenz's law questions. So we have here a coil, and you should also pay attention to the way it is wound on this. It's behind the core and coming out. Okay. So there is a coil, there's no battery here. But we do something, we take a magnet. This is the south pole, this is the north pole. You know what happens, right? From the north pole, the magnetic field line will be out. At the south pole, the magnetic field line will be coming to it. Now you are moving the magnet away from that coil. You are moving the magnet away from the coil. So that means the magnetic flux through this coil is changing. Lenz's law will come into action. Lenz's law says it will oppose this change. The effect that is produced there is a magnetic field to the left, and that magnetic field is decreasing, still to the left but become less. There is a magnetic field in the coil to the left, and it is decreasing in magnitude. The coil doesn't like it. It will try to oppose this. How can you oppose it? How can you oppose it? It should produce a magnetic field to stop this change. What kind of change we have? There is a magnetic field to the left and it is decreasing. So I will not allow it to decrease. I will produce my induced magnetic field in the same direction. That's how I can stop it, oppose it. So the induced magnetic field from the coil also must be to the left. So I am opposing this effect. That is the Lenz's law. There is a magnetic field to the left from outside and it is decreasing. I don't want it to decrease. So how can I stop it? Produce my own induced magnetic field also to the left. Okay, next step. So if I have to create a magnetic field to the left, which direction should the current flow in the coil? Looking from this side, should it flow clockwise or counterclockwise? Clockwise will give the magnetic field to the right. I want the magnetic field to the left. So I should flow, looking from this side, counterclockwise. So that means the current should flow like this, right? You understand that? I want to produce a magnetic field to the left. It will happen only if the current flows like this. Look at the thumb. Thumb shows you the magnetic field direction. So that means the current direction through R will be from A to B. Consider the arrangement shown in the figure where R is equal to 5.5, L is equal to 1.4, B is equal to 2.25. If the bar is moved with the speed of 2.44 meter per second, the induced current in the loop is, okay, so we have the R, we have the length, and we have the magnetic field, and we have the speed. You should remember this is the motional EMF. When you have a bar crossing the magnetic field line, so what happens is it will create an EMF given by, this is in the formula sheet, VBL. This is the velocity perpendicular to the magnetic field, and L is the length of the bar that is being moved. So you need to know which equation to pick. So this much of EMF will be produced, but the question is to find the current. So you have to divide by the resistance. Because it's like there is a battery here that will start sending a current. So the current will be EMF of the battery divided by resistance. So all you have to do is to substitute. These are all given, and you'll get the answer. You have everything, make sure everything is in SI unit. Velocity 2.44, it is in SI unit. Magnetic field 2.25 Tesla, that is in SI unit. L is 1.4 meters, that is in SI unit. R is in ohms, that is also SI unit. Okay, that's it. Substitute and get the answer. you should get this answer. Number 25. A current decreasing at the rate of 9.6 amperes per second is flowing through the solenoid having no appreciable resistance. The self-induced EMF in the solenoid is found to be 8.4 volt. What is the self-inductance of the solenoid? So can somebody tell me the equation needed here? This is where you are talking about the self-inductance. The definition of the self-inductance, can you tell me? Check your formula. We say the EMF on the coil, the back EMF from the inductor will be minus L is proportional to the rate of change of current. This is how you define the self-inductance of the coil. So this is the equation. You see that? Okay. So we need everything. The EMF of the solenoid is 8.4. So you put 8.4 here. And this is given. The current is changing at the rate of amperes per second. So you put substitute, you'll find the L. You can ignore the negative sign. Okay, that is just a magnitude of E divided by rate of change of current is equal to the self-inductance. So make sure everything in SI unit. Yes, volt is SI unit, ampere per second is SI unit. So you should get this answer. It will come out in Henry. If you put everything in SI unit, the inductance will be in Henry. Henry is the SI unit for inductance. Number 26. The 60 millihenry ideal inductor is connected in series with the 60 ohm resistor through an ideal 15 volt DC power supply and an open switch. If the switch is closed at time t equal to 0, what is the current at t is equal to 10 millisecond? It is somewhat like our RC circuit, but instead of C, we have an L, okay? No capacitor, but an inductor. So how do we answer this question? Nawaf? How do you answer this question? Hmm? Sorry? Why? Pick the formula sheet, tell me. Now we have a LR circuit, not LC circuit, not RC circuit, but RL circuit. When you close the switch, the current against the time will start from 0 and it will increase like this. And this has an equation. What is that equation? The curve, current versus time. For an LR circuit, there's a current versus time equation. Check your formula sheet. Can't you find it from the formula sheet? I'm helping you. Is there any equation there which gives you I as a function of time? And there is even description. And I make the formula sheet by chapter, don't I? The final exam formula sheet. Can't you still see it? There is even description. We are in chapter 20. Which is okay. So that's the equation that give I as a function of time, where this tau is called the time constant, like in the RC circuit. For RL circuit also, we have a time constant. For RC circuit, it is R tau is equal to RC, but RL circuit, the tau is equal to L over R. That's the theory. So we come here, you write the equation. I max is tau, this is the time, this is the time constant. Is the square? No. Can you do it for me? I know the answer is there, but tell me what to do. Substitute the value, see whether you get the answer. What should I write for I? That is the question. The question is, find I when the time is 10 millisecond. So it is not solving equation, it's just calculating this quantity. You have to calculate this quantity. So what is I max? So if you go back to the formula, I max is equal to E over R. Okay, it is already there. So let me rewrite the equation again. This is the current, it will come eventually. Okay, it will not come to this current at once. It's as if it is not there at all, we'd expect the current to be simply E divided by R, but it will not reach the E divided by R at once. Because of this inductor, it will resist this current to develop immediately. It will only reach the eventual current after some time. Tau is equal to L over R. Now you substitute. Okay, tell me. E over R. Maybe you can start this and put the E over R. How much is E? 15. Okay. How much is R? 6. Come on. Multiply, start the bracket, 1, subtract. How do you get this E to the power? Shift lin. Shift lin, okay, not log. Then you put this again, this up and down fraction. You need the negative sign. Don't forget that. It's very important. Negative sign. Time. Time is how much? 10 millisecond. Yeah. Yeah. Okay. Yeah, you can do that. 0. I don't know if maybe it is better for me to tell this now. Let me pause there. See, L over R, right? That is the time constant. Time constant should be in second. L over R, the answer will be in second. If I put L in millihenry, and R in ohms, Henry per ohm is second. Okay, if you put Henry and ohm, it will be in second. I like to keep it in millisecond. I'll tell you why in a minute, okay? Why? I'll tell you later why. But I like to keep this in milliseconds, so I will not convert the 60 millihenry to Henry. I will keep it as in millihenry. So how much is this? Tau is equal to 10 millisecond. Okay. All right. Are you following me? Is second how much? It will be 10 to the power minus 10 to the power 3, right? But let me keep it in millisecond. Why? I will put the time in millisecond. I will write this also in milliseconds. So I don't, it's a ratio. I don't have to do conversion again. So that's why. So where is my calculator? So I will put this time in millisecond, and I will also write the tau also in, this also happens to be, I made the question such that they are equal. That's it. You click the equal. This is not a solving equation, right? It's a calculating an expression, standard calculation. 1.58 to two significant figures, it will be 1.6. The 3 ampere current passes through the inductor, through an inductor. If the inductor stores 2 joules of energy, what is the inductance? Go and tell me the equation, please. Check your formula sheet and tell me what the equation is. It's an easy, straightforward question. What's the equation we should use? Energy is equal to energy. What did you say? Find the equation for this question. What is the equation? Energy. The equation for the energy. Come on, guys. Even the description is there. Okay? So the energy is half Li squared. Potential energy, electrical energy, half magnetic field. So this is given 20. Inductance is the unknown. I is 3 amperes. Solve this. Get the value of L. Should get 4.4 Henry. The RMS current is equal to, so now we are coming to chapter 21. RMS current is the B. It's, RMS current is AC current is not a constant current. It just fluctuates. So you can say it is a direct current that dissipates an equal amount of energy in a resistor at the same rate as an AC current. That's how you get the average value of this AC current. Okay. Question 29. In an inductor, in an AC circuit, right, these are the things that you need to remember. That will not be in the formula sheet. Inductor potential difference, the voltage across the inductor will be leading the current by, in an AC circuit, by 90 degrees. What about the capacitor? Voltage across the capacitor will be lagging the current by, behind the current by 90 degrees. What about the resistor? The difference between current and the voltage. No difference. It will be in phase, 0 degree. Okay, so this we are talking about the inductor. The answer is B. Voltage will lead the current by 90 degrees. Question number 30. A generator delivers an AC voltage of the form delta V is equal to 68 sine 45 pi t to a capacitor. The maximum current in the circuit is 0.76 ampere. Find the value of the capacitance. Okay, can you tell me the equation by looking at the formula sheet? Any clue from the formula sheet? Ohm's law. So here, although it is in RMS, I can do it with the, here the maximum current, right? So I can say that voltage is equal to current into reactance. Instead of R, you have to write the reactance of the capacitor, so Xc. So it is valid for RMS or maximum. So here the value we getting is the maximum voltage, this one. So I would say delta V max is equal to I max. So the current voltage maximum is this and the maximum current is this. So we know this, we know this. So we can get the reactance. So the reactance will be 68 divided by I max, which is 0.76. But that's not the answer yet, because the question is find the value of the capacitance. So now you have to remember reactance, capacitive reactance is given by this equation. So this is the omega. Okay, so I can also write. This is the omega part, okay, the omega. So in terms of omega, so now we have the answer. For XC, we will say 68 divided by 0.76 equal to 1 over omega is 45 pi (68) divided by 0.76 equal to 1 over omega is, this is the omega, 45 pi, and C. Solve this. Take the calculator. And put the values in. 68 divided by 0.76 equals, can make another fraction, 1 come down 45 pi. You use the pi from the calculator. Multiply by, this is the unknown. What do you do for the unknown? X. Solve it. Shift calc 7.9. Okay, that's correct. You know why? So what did I get from the calculator? C is equal to 7, 9, 10 to the minus 5 farad, right? So I can write it as 79 10 to the minus 6 farad. You understand what I did? Okay, which is equal to 79 microfarad. So the answer. The current in an inductor is connected to an AC voltage source, lags the voltage. This lag is caused by the back EMF of the coil. Okay, it's just a statement question, because what the back EMF will try to reduce the current to 0. Meanwhile, the EMF across the inductor is maximum. So the voltage is ahead of the current by 90 degrees because of the back EMF in the coil. A resistor is connected in series with a capacitor and a generator having maximum voltage of 120 volt and operating at 60 hertz. As this frequency, the capacitive reactance XC of the capacitor is this much, find the maximum current in the circuit. So again, you should find the formulas in the formula sheet, chapter 21. So it is the Ohm's law. Ohm's law tells you the voltage delta V is equal to I into impedance. Now I have to say impedance. If it is resistance only, I can put R. If it is reactance only, I can put X. Here we have both resistance and reactance together. So the impedance. So delta V is 120 volt. This is the RMS value. Oh no, maximum. not RMS value, maximum value. So I should write in terms of maximum value. The question is to find this. This is given. Okay, let's see. What is impedance? In general, you can write this for a LRC when you have L as well, but there is no L here. If you just remember this as in general, there is no L now. This is 0. No inductor, that is 0. So we have only XC. So that will make this look at this equation. We know everything except I max. So you take your calculator, solve it. Let me put the values in. 120 squared equal to I max is our unknown, multiplied by R is 56 and XC is 120. Oh, I cannot write anything there. Okay, plus 120. Is it 120? No, 82.9. Squared and close the bracket and solve for I max. Can you do it on your own and give me, check the answer, whether you get the correct answer? Delta V is 120. R is 82, no, 56. XC is 82.9. Do it in a solving mode. Type the equation. How much delta V? 120 equals I max is our unknown, multiplied by square root. R squared is 56 square plus XC is 82.9. Okay, that's it. Shift calc 1.19, which is 1.2. All right, this one. Consider RLC circuit with R, XL, XC. The circuit is connected to 10 with RMS and 600 Hz AC source. Find the average power. Okay, so we need the equation for the power. Can you tell me the equation? That's it, right? But we don't have the current, do we? We don't have the current. So what do you do? The power in a circuit is this. I squared RMS, we don't have the I, we don't have the I. Well, the power delivered, we have to get it in terms of this. IRMS squared into R, IRMS in delta VR. Okay, so how do you get the current? This is equal to delta V RMS divided by Z. Z is R squared plus XL minus XC whole thing squared multiplied by current. So in terms of the current, so this squared into R. P average is equal to I squared RMS into R. Calculate that. I will leave it to you to calculate. Let me finish the other two questions. So that's the equation. 34. A series RLC circuit has resistance, inductance. The voltage source operates the frequency of that, which is the resonance frequency of the circuit. Find the circuit's capacitance. So resonance happens at this. That's it. I think we have this, and we have L. The only unknown is C. So you solve for C. This is the last one. What is the impedance of a series RLC circuit or resonance? When the resonance happens, the impedance is the minimum. The impedance is given by this. The minimum, because R is a constant, it doesn't change when you change the frequency. Resonance happens when this is equal to this. XL is equal to XC. When that happens, Z will become, because in XL equal to XC, this is 0, so the Z will become R. The impedance of a series RLC circuit at resonance will be simply the resistance.